the next thing we want to talk about is just a little bit more about area, because you might understand that the formula for area for polar graphing is really beautiful. 1/2 r squared d theta from theta sub 1 to theta sub 2. But often you have problems where you are looking for the area inside one and outside another. So this is question 26. So we're looking for the area that lies inside this limacon, this dimpled limacon, 2 plus sine theta, and outside the circle. And that's pretty simple because the circle in its entirety is inside of this this limacon. So I just need to find the area of the limacon. Let's see. So I'm just going to take this from 0 to 2 pi. That's how much the thetas I need to roll through in order to get that whole limacon. And I'm going to have 2 plus sine theta squared d theta, and I'm going to subtract that whole circle. And in fact, I don't even have to really do this because I know I can figure out the area of that circle. But let's do this anyway. That's, let's see, from 0 to, well, that's just 0 to pi, isn't it? That's just 0 to pi. Okay, so then we do what we need to do for that. Here's where it gets a little trickier, though. The other one I want to talk about is this. So question 24 in your textbook is inside r is 1 minus sine theta, and outside r is 1. Excuse me, I do not have coronavirus. So our area, well, let's see what this looks like. 1 minus sine theta. Well, r is equal to 1 is just a circle. Center at the origin, radius 1. 1 minus sine theta is a cardioid. So we're looking for everything that's inside here, but not inside the circle. So it really is, let's see, I need to figure out what's going on. Let's see, my theta value over here is going to be pi. So my area is going to go from 1/2, and I'm going to start at pi and go all the way to 2 pi, because that's the region that I need to have my theta run through in order to sweep out this area. And what I'm looking for is the area of, well, just part of a sector. And this is very much akin to when we were finding area between two curves. So my outer sector would be 1/2, 1 minus sine theta quantity squared. But then from that, I need to take 1/2, well, this little sector is 1/2 just 1 d theta. So let's see what that looks like. So we're going to have 1/2, we're going to go from pi to 2 pi. We're going to have 1 minus 2 sine theta plus sine squared theta minus 1 d theta, which is just going to give us 1/2. We're going to go from pi to 2 pi, and we're just going to end up with sine squared theta minus 2 sine theta d theta. This 2 sine theta we can handle. Sine squared theta, we have to use that trick again, right? We know that cosine of 2 theta, that double angle formula, is cosine squared minus sine squared. So that could be written as 1 minus 2 sine squared theta. So 2 sine squared of theta is equal to 1 minus cosine 2 theta. So sine squared of theta, I am going to rewrite as 1/2 minus 1/2 cosine of 2 theta. All right. So this becomes 1/2 minus 1/2 cosine 2 theta minus 2 sine theta d theta. We haven't taken an antiderivative yet. Pi to 2 pi. So we're going to have 1/2 theta minus, let's see, 1/4 sine of 2 theta plus 2 cosine theta, all between pi and 2 pi. And let's see what that gives us. We're going to have 1/2. We're going to have pi minus 1/4 of the sine of 4 pi, which is 0. We're going to have 2 cosine 2 pi, which becomes 2. From that, we're going to subtract pi over 2, And then we're going to have sine of 2 pi over 0, and cosine of pi is -1, so that's -2. So that gives us 1/2, goodness gracious, pi plus 2 minus pi over 2 plus 2, 1/2, 4 plus pi over 2. So it looks like it's going to give us 2 plus pi over 4 as our area.